We tend to view the history of life on Earth as a resilient, upward climb. We assume that once an ecosystem is built, it possesses an inherent stability, a sheer inertia of diversity that protects it from collapse. But 252 million years ago, that illusion was violently shattered. In a geological heartbeat, the teeming reefs, the crinoid meadows, and the endless forests of the Permian world were erased. They were replaced by a global shroud of black, sulfitic mud. This was the Great Dying, a catastrophe so absolute that it suffocated the vast majority of marine life and nearly reduced our planet to a sterile, silent rock. It stands as the darkest chapter in the biography of life, a moment when the Earth's own life support systems were weaponized against the biosphere. For generations, the true nature of this extinction was obscured by the limitations of our ability to measure deep time. In the fossil record, the difference between a catastrophe that unfolds over 1,000,000 years and one that happens in a single decade can be impossible to discern with the naked eye. Without a stopwatch, paleontologists could not determine if the Great Dying was the result of a slow, grinding failure of the environment or a sudden, violent shock. The resolution to this mystery lies locked inside the crystal lattice of a mineral called zircon. Zircons are the black boxes of the geological record. Formed within cooling magma, these microscopic crystals are incredibly durable, surviving the erosion and metamorphism that destroy other rock types. Crucially, they act as perfect clocks. When a zircon crystal forms from molten rock, it incorporates uranium atoms into its structure but physically rejects lead atoms. Therefore, any lead found inside a zircon today can only be the product of radioactive decay that occurred after the crystal hardened. By measuring the ratio of uranium-238 to lead-206, geochronologists can calculate the age of the crystal with a margin of error of less than 0.1%. Recent application of high-precision uranium-lead dating to the Permian Triassic boundary has revolutionized our understanding of the event. The data reveal that the primary pulse of the extinction occurred within a window of fewer than 60,000 years. In the context of 4.5 billion years of Earth's history, this is instantaneous. It is a gunshot wound. This extreme speed forces us to abandon theories of slow climate shifts, gradual sea level changes, or shifting tectonic plates. The trigger had to be massive, global, and incredibly rapid. The dating confirms that this window coincides perfectly with the main eruptive phase of the Siberian Traps. The Siberian Traps' large igneous province is not a volcano in the conventional sense. It was a flood basalt event of apocalyptic proportions. The eruption did not spew from a single cone, but poured from deep fissures in the Earth's crust, flooding 7 million square kilometers of present-day Siberia with lava. The total volume of ejected rock is estimated between 7 million and 15 million cubic kilometers. If this lava were spread evenly over the entire continental United States, it would bury the land under a layer of rock more than 1 kilometer thick. However, the geological record shows that Earth has survived other flood basalt events without facing near-total sterilization. The unique lethality of the Siberian Traps was not determined by the volume of the lava, but by the specific geology of the crust that the lava moved through. The magma rose through the Tunguska Basin, a massive sedimentary depression loaded with the accumulated hydrocarbon wealth of the Carboniferous and Permian periods. The basin was packed with thick seams of coal, reservoirs of oil and gas, and extensive layers of evaporate salts, like anhydrite and halite. The magma did not merely flow over these deposits, it intruded into them. Much of the molten rock never reached the surface, instead stalling underground to form vast horizontal sheets known as sills. These sills, extending for thousands of kilometers through the sedimentary rock, acted as subterranean heating elements. They baked the coal and organic shales to temperatures exceeding 1100 degrees Celsius. This process, known as contact metamorphism, transformed the Tunguska Basin into a continent-sized combustion engine. It did not just release volcanic gases, it burned the Earth's buried fossil fuel reserves, generating a pulse of greenhouse gases and toxins that would overwhelm the planet's atmospheric defenses. The forensic evidence of this combustion is preserved in the atomic signature of the rocks themselves. Carbon, the building block of life, exists in two stable isotopes, the lighter carbon-12 and the heavier carbon-13. Biological processes, from photosynthesis to shell building, prefer carbon-12. Consequently, living things and the fossil fuels derived from them are enriched in this lighter isotope, while the mantle and inorganic limestones contain a higher proportion of carbon-13. At the exact horizon of the extinction, the global geological record displays a violent shift in this ratio, known as a negative carbon isotope excursion. The amount of carbon-13 relative to carbon-12 plummets. This shift is so massive and so sharp that it cannot be explained by the release of mantle carbon alone. Volcanic gases are simply not light enough to skew the global budget this dramatically. Mathematical modeling of the carbon cycle dictates that the only way to produce such a profound excursion is to inject trillions of tons of isotopically light organic carbon into the atmosphere. This is the smoking gun that proves the Siberian Traps were burning coal. Field geologists working in Siberia have found direct physical proof of this interaction. They have documented halos of metamorphosed coal surrounding the basalt sills, zones where the coal has been devolatilized or turned into graphite by the intense heat. Furthermore, researchers analyzing Permian Triassic boundary sediments in the Canadian Arctic, thousands of kilometers away from the eruption, have discovered microscopic spheres of carbon known as fly ash. These particles are structurally identical to the fly ash produced by modern industrial coal-burning power plants. Their presence in the geological record confirms that the Siberian eruption was effectively a natural industrial accident, spewing particulate matter and soot across the entire northern hemisphere. This combustion released far more than just carbon dioxide. The heating of the Tunguska evaporite salts mobilized massive quantities of volatile halogens, including chlorine, fluorine, and bromine, as well as toxic heavy metals like mercury. These gases rose into the stratosphere, where they initiated a catalytic destruction of the ozone layer. Unlike the seasonal ozone thinning we observe today, the Permian ozone collapse was global and sustained. The loss of this protective shield allowed high-energy ultraviolet B radiation to bombard the surface of the planet. The biological cost of this radiation is recorded in the fossilized reproductive cells of plants. Paleontologists, scientists who study pollen and spores, have documented a worldwide surge in aberrant pollen at the extinction boundary. Under normal conditions, plant pollen separates into individual grains. At the boundary, the record is filled with tetrads, clusters of 4 grains that failed to separate, and grains with malformed spines and walls. These specific deformities are the hallmark of DNA damage caused by ultraviolet B radiation. The trees of the Permian were being genetically mutilated by the sun. This phenomenon, known as mutagenesis, drastically reduced seed viability and stunted plant growth, triggering a collapse of the terrestrial flora. Simultaneously, the release of sulfur dioxide from the burning coal and evaporites generated catastrophic acid rain. While sulfur aerosols typically have a short residence time in the atmosphere, the pulsed nature of the Siberian eruptions meant that the Earth was subjected to repeated, intense acid storms. This precipitation acidified freshwater ecosystems, devastating amphibian populations and insect larvae. On land, the combination of acid rain and the death of the forests led to a total failure of soil cohesion. Plants act as the skin of the continents. Without their root systems to bind the earth, the violent rains strip the landscape down to the bedrock. This process, known as the mud drape, is visible in the rock record as a sudden influx of terrestrial sediment into the marine environment. The oceans were not only heating up, they were being choked by the washing away of the continents. This erosion delivered a massive pulse of nutrients, nitrogen and phosphorus, into the coastal waters. This process, called eutrophication, would act as the catalyst for the next phase of the disaster, turning the oceans from a sanctuary into a trap. As the concentration of atmospheric carbon dioxide skyrocketed from roughly 400 parts per million to values exceeding 2,500 parts per million, the Earth experienced a runaway greenhouse effect. Sea surface temperatures in the tropics rose by 10 to 15 degrees Celsius. This rapid warming fundamentally broke the physical chemistry of the ocean. According to Henry's law, the amount of gas that can dissolve in a liquid is inversely proportional to its temperature. As the ocean water warmed, it lost its capacity to hold dissolved oxygen. Simultaneously, the global ocean circulation system, which relies on temperature gradients to mix oxygen-rich surface water with the deep abyss, began to stall. The result was a global stagnation. The ocean became stratified, like a pond that has sat still for too long. Into this stagnant, warming water, the eroding continents dumped their nutrient load. This fertilizer triggered massive blooms of algae and bacteria, which consumed what little oxygen remained. The oceans transitioned into a state of euxenia, a deadly condition where the water is both anoxic, meaning devoid of oxygen, and sulfidic, meaning rich in hydrogen sulfide. In the modern world, euxenia is rare, found only in isolated, oxygen-starved basins like the Black Sea. During the end Permian extinction, this toxic water expanded from the seafloor, rising up the continental shelves and eventually breaching the photic zone, the sunlit surface layer. The evidence for this purple ocean comes from the molecular fossils of the microbes themselves. Geochemists analyzing rocks from the boundary have detected specific biomarkers called isoreneurethane and ochanon. These complex organic molecules are the breakdown products of pigments used exclusively by the chlorobiaceae, or green sulfur bacteria, and the chromatiaceae, or purple sulfur bacteria. These organisms have a very specific set of requirements for survival. Finding these biomarkers in sedimentary rocks formed in shallow waters is a revelation. It proves that the boundary between the oxygenated world and the hydrogen sulfide world had risen all the way to the surface. Vast stretches of the Panthalassic and Tethys oceans would have been stained a bruised purple or sickly green by these bacterial blooms. These microbes effectively terraformed the ocean into a toxic environment. Worse, these bacteria released bubbles of hydrogen sulfide gas into the atmosphere. Hydrogen sulfide is lethal to eukaryotic life. Even in small concentrations, it disrupts the mitochondrial electron transport chain, effectively turning off the power plant of the cell. The release of this gas would have poisoned coastal ecosystems and added another layer of toxicity to an atmosphere already choked with carbon dioxide and acid rain. In the tropical oceans, the heat itself became a direct killer. Oxygen isotope data derived from the fossilized teeth of conodonts, eel-like marine organisms, indicates that sea surface temperatures in the equatorial Tethys Ocean exceeded 40 degrees Celsius. This is the temperature of a hot bath. At 40 degrees, the proteins in most multicellular animals begin to denature, losing their shape and function. Mitochondria fail, and the metabolic machinery of life grinds to a halt. The tropics became a biological dead zone, a thermal barrier that severed the connection between the northern and southern hemispheres. Marine animals were forced to migrate toward the poles in a desperate bid for cooler water, but even there, they found no safety, for the chemistry of the water itself was turning against them. While the physical environment of the ocean became hot and breathless, its chemical balance was undergoing a silent, corrosive collapse. The oceans are the planet's primary carbon sink, absorbing a significant portion of the carbon dioxide released into the atmosphere. But this absorption comes at a cost. When carbon dioxide dissolves in seawater, it reacts to form carbonic acid. This acid dissociates, releasing hydrogen ions that lower the pH of the water. During the height of the Siberian Traps emissions, the rate of carbon injection was so fast that it overwhelmed the ocean's natural buffering capacity. The pH of the global ocean dropped by approximately 0.6 to 0.7 units. In the logarithmic scale of pH, this represents a massive catastrophic increase in acidity. This acidification fundamentally altered the saturation state of calcium carbonate, the mineral that countless marine organisms use to build their shells and skeletons. Marine calcifiers, such as corals, clams, and brachiopods, rely on the water being supersaturated with carbonate ions. As the ocean acidified, the excess hydrogen ions bonded with the carbonate ions, effectively locking them away. The saturation state dropped below 1.0, meaning the water became undersaturated. In these conditions, seawater becomes corrosive to calcium carbonate. For a creature living in this water, the metabolic cost of building a shell skyrockets. Energy that should be used for feeding, growing, or reproducing must be diverted simply to prevent their skeletons from dissolving into the water. The extinction record shows a ruthless physiological selectivity that perfectly matches this acidification model. The Great Dying did not kill randomly. It targeted organisms based on their ability to regulate their internal chemistry. The hardest hit were the physiologically unbuffered organisms. This included the rugose and tabulate corals, which built massive calcite reefs, and the articulate brachiopods, which dominated the Paleozoic seafloor. These animals relied on passive diffusion for respiration and had limited control over their internal fluids. When the external ocean turned acidic, their internal tissues followed suit, leading to respiratory acidosis and metabolic failure. The rugose and tabulate corals were driven to total extinction, vanishing from the face of the earth. In contrast, the survivors were organisms that possessed buffered physiologies. Animals like gastropods, bivalves, and early crustaceans possessed active gills and muscular circulatory systems. These adaptations allowed them to actively pump ions across their cell membranes, maintaining a stable internal pH even as the surrounding ocean turned sour. They survived not because they were larger or stronger, but because they had the physiological machinery to withstand the chemical assault. This selective pressure effectively reset the evolutionary trajectory of the oceans, clearing away the stationary, filter-feeding fauna of the Paleozoic and paving the way for the mobile, active, modern evolutionary fauna that fills our oceans today. When the volcanic fury of the Siberian Traps finally subsided, it left behind a world that was broken. The recovery from the Great Dying was not a rapid bounce back. It was a prolonged 10 million year struggle through a hostile environment. This interval, comprising the entirety of the early Triassic period, is marked by a stark anomaly in the geological record known as the coal gap. For millions of years before the extinction, the Earth's continents were covered in vast peat-forming forests that eventually compressed into coal. At the Permian-Triassic boundary, coal deposits vanish worldwide. They do not reappear until the Middle Triassic, roughly 10 million years later. This gap signifies the total absence of complex forest ecosystems. The great Glossopteris swamps of the south and the conifer forests of the north were obliterated. In their place, the land was colonized by disaster vegetation. The early Triassic landscape was dominated by a monotonous scrub of quillworts and herbaceous lycopods. These were weedy, opportunistic plants capable of rapid reproduction and tolerant of the degraded, unstable soils. They formed a low, sparse ground cover that offered little in the way of food or shelter for terrestrial animals. The breakdown of the forest ecosystems is further highlighted by the fungal spike. In the immediate aftermath of the extinction, rock layers contain a massive abundance of microfossils known as reduviasporanites. Originally interpreted as fungal spores feeding on the rotting corpse of the world's forests, newer research suggests these may be stress-tolerant freshwater algae, or a transitional fungal algal form. Regardless of their exact classification, their ubiquity signals a collapse of primary productivity and a world dominated by decay and stagnation. The oceans mirrored this desolation. With the extinction of the reef-building corals, the seabed was taken over by microbial mats. These slimy, bacterial carpets coated the shallow seafloors, a throwback to the Precambrian era before the evolution of animals. The complex three-dimensional structures of the reefs were gone, replaced by two-dimensional flats of mud and slime. The animals that did manage to survive in this impoverished world were subjected to the Lilliput effect. Across the board, from shellfish to reptiles, the survivors were significantly smaller than their ancestors. This dramatic reduction in body size was a direct physiological response to the chronic environmental stress. Smaller animals have a higher surface area to volume ratio, allowing them to shed heat more efficiently in the sweltering climate. They also require less food and oxygen, a critical advantage in a world where primary productivity had collapsed and the air was thin. The persistence of the Lilliput effect for millions of years indicates that the lethal conditions, the heat, the low oxygen, the acidity, did not vanish overnight, but lingered, keeping life in a chokehold long after the volcanoes fell silent. In the ruins of the Paleozoic world, a new cast of characters emerged, defined not by their dominance, but by their resilience. The unlikely ruler of the early Triassic was a pig-sized herbivorous relative of mammals called Lystrosaurus. In the absence of competitors and predators, this unassuming animal exploded in abundance, at one point comprising 95% of all terrestrial vertebrates. Lystrosaurus was the ultimate disaster taxon. Its anatomy and behavior were perfectly tuned to the wasteland. It possessed a powerful, turtle-like beak capable of shearing through the tough, fibrous disaster vegetation that other animals couldn't eat. Crucially, Lystrosaurus was a burrower. Fossil evidence shows these animals curled up inside underground dens. By living subterranean lives, they could escape the lethal surface temperatures and the sterilizing ultraviolet radiation that still bathed the planet. Bone histology reveals that they grew rapidly and bred at a young age, a live fast, die young strategy that allowed their populations to recover quickly from the frequent environmental crises of the Triassic. In the oxygen-starved oceans, the ecological niche of the vanished brachiopods was seized by a bivalve named Chloria. While the heavy-shelled brachiopods dissolved, Chloria thrived. Its secret was its shape. It was exceptionally flat and paper-thin. This morphology maximized its surface area relative to its body mass, allowing it to act like a living sponge, absorbing what little oxygen existed in the hypoxic waters. It was a specialist in suffocation, blooming in vast numbers across the stagnant seafloors. But the most consequential survivors were a small, obscure group of reptiles known as the archosaurs. In the early Triassic, animals like Proterosuchus, a crocodile-like predator with a hooked snout, began to diversify. The success of the archosaurs, the lineage that would eventually produce dinosaurs, birds, and crocodiles, may be linked to a specific anatomical advantage: their lungs. Unlike the synapsids, the ancestors of mammals, which relied on a tidal breathing system where air flows in and out the same way, the archosaurs evolved a unidirectional flow respiratory system. Similar to the breathing of modern birds, this design ensures that air flows through the lungs in one continuous loop, allowing for a much more efficient extraction of oxygen. In the hypoxic, low-oxygen atmosphere of the Triassic, this gave the archosaurs a metabolic supercharge. They could remain active and predatory in the air that would leave a synapsid gasping. This hypoxia advantage fundamentally shifted the balance of power on Earth. For tens of millions of years during the Permian, the synapsids had been the dominant land animals. But the Great Dying broke their hegemony. The low-oxygen world favored the efficient lungs of the archosaurs, allowing them to grow larger, faster, and more diverse. This physiological edge cleared the ecological stage for the rise of the dinosaurs, relegating the surviving mammals to the shadows for the next 150 million years. The Permian-Triassic extinction was not just a tragic loss of life. It was a systemic filter that redefined the rules of survival. It ended the ancient, stable world of the Paleozoic and ushered in the dynamic, high-energy world of the Mesozoic. The survivors passed through this bottleneck, not because they were the strongest, but because they happened to possess the specific traits, burrowing, buffering, and breathing, required to endure a hot, acid, suffocating planet. The Great Dying stands as a grim monument to the fragility of the biosphere, a testament to how quickly the Earth's life support systems can be dismantled when the carbon cycle is broken.